Module 8, Lecture A, Distribution Basics. By the end of this lecture, you will be able to describe the main tf.distribute strategies available in TensorFlow 2.20.0 and their typical use cases, explain how data parallelism and replica synchronization work in distributed training, and identify the changes required in model and input code to support distribution strategies. Core distribution strategies. Single host mirrored strategy. Single host mirrored strategy in TensorFlow lets you scale training across multiple GPUs on one machine using data parallelism. It creates a copy of your model on each GPU, splits each training batch into slices, and processes those slices in parallel. After each step, it aggregates and usually averages the gradients so all model copies stay synchronized. This makes it easy to move from one GPU to several with minimal code changes while keeping a simple single machine workflow, which is ideal when you have multiple GPUs on a single node and do not want the complexity of multi-machine setups. Single host mirrored strategy lets you speed up training by using multiple GPUs on one machine without changing your existing workflow. You can scale a convolutional neural network from one GPU to several to process more images per step and shorten each epoch, or fine-tune a transformer model faster by spreading the work across GPUs. Because all replicas share the same host memory and storage, data pipelines and checkpoints are easy to manage, which makes this approach especially accessible for people new to distributed training. Single host mirrored strategy is a good starting point for parallel training on a single, well-equipped server because it synchronizes gradients efficiently across multiple GPUs using high-speed connections. It works smoothly with TensorFlow's higher-level interfaces, so you can often adapt existing code with only minor changes while benefiting from automatic device management. The main limitation is that everything runs on one machine, so you are constrained by that system's CPU, memory, and overall capacity. As your datasets or models grow larger, you may eventually need more advanced distributed strategies beyond a single host setup. Python code, single host mirrored strategy. This script introduces the basics of single host mirrored strategy by comparing training on a single GPU or CPU with training on multiple GPUs using mirroring. Its goal is to highlight how distribution works across devices while keeping the output concise. By contrasting single device and mirrored multi-GPU runs, it shows the key behavior of distributed training without overwhelming detail. A line that starts with an exclamation mark is a shell command used to install a specific TensorFlow version, in this case, version 2.20.0. It is not Python code, but a command run in the system environment. Installing a fixed version is important because different TensorFlow versions can change features and behavior. By specifying the version, you help ensure the script runs consistently and remains compatible with the rest of the code. This code begins by importing three key Python libraries. It brings in the operating system library to interact with the system, such as working with files or environment settings. It then imports the random library to generate random numbers, which is useful for tasks like shuffling data. Finally, it imports NumPy, a numerical computing library commonly used to handle arrays and perform efficient mathematical operations. We start by importing TensorFlow, which we use to build and train machine learning models. From TensorFlow, we then import the Keras module, a high-level interface that simplifies creating and training neural networks. Finally, we import the layers component from Keras, which provides the different types of neural network layers used to construct a model. Together, these imports provide the core tools needed to define the network architecture and manage the training process. We set a seed value, such as 42, so that any random operations in our code give the same results every time, which is important for reproducibility. To achieve this, we set the seed for the random library, then for NumPy, and then for TensorFlow. Using the same seed across these libraries keeps our experiments consistent and makes it easier to compare and repeat results reliably. This line of code displays the version of TensorFlow that is currently in use. It provides a quick check that the correct version is installed. Confirming the version helps ensure that the rest of the code will run correctly and be compatible with the installed library. The code first checks which graphics processing units, or GPUs, are available on the system using TensorFlow's device configuration tools. It creates a list of all detected physical GPUs and then counts how many are present. Finally, it prints this number so you can see whether the system has no GPU, a single GPU, or multiple GPUs. This information is used to decide if you should run training on one device or use a mirrored strategy across several GPUs for distributed training. The code checks how many GPUs are available and chooses a training strategy based on that. If more than one GPU is detected, it uses a mirrored strategy that enables distributed training across multiple GPUs. If there is only one GPU or none, it falls back to a default strategy designed for single-device training. The selected strategy is then saved in a variable for use later in the training process. The code reports which distribution strategy is being used for training the model, such as mirrored strategy when multiple GPUs are available, or default strategy when they are not. It also prints how many replicas are running in sync, meaning how many copies of the model are training at the same time across devices. This information helps you understand how training is distributed and confirm that the model is using the available hardware as intended. This code uses Keras tools to load the MNIST dataset, which is a standard collection of handwritten digit images used to train image recognition models. The data is divided into images and their corresponding digit labels. Only the training portion of the dataset is kept and used in this example, while the test portion is intentionally ignored to focus on demonstrating work with the training data. For this quick demonstration, the training dataset is intentionally reduced in size. The code keeps only the first 6,000 samples from the original training data, including both the images and their labels. Using this smaller subset speeds up training and makes the process easier to run and observe in a short example. The goal is to show how the model works without the time and resources required for the full dataset. The code first converts the training images to a 32-bit floating point format so they work properly with TensorFlow operations. It then rescales the pixel values from their original range of 0 to 255 down to a range between 0 and 1. This normalization standardizes the input data and helps the model train more effectively by improving its convergence during learning. We expand the dimensions of the training data to add a channel dimension, so it matches what convolutional layers expect. Convolutional neural networks require input data to include a CHO axis in addition to height and width. MNIST images are grayscale, so they start with only height and width. By using a function that adds an extra dimension for the single color channel, we make the image data compatible with the convolutional layers that will process it. Before building the dataset, the code prints the shapes of the training data and labels to confirm the data is organized correctly. It checks that the training data has the expected dimensions of 6,000 images, each with 28 by 28 pixels and a single channel. It also verifies that the labels have the same number of entries as there are training samples, ensuring every image has a matching label. We begin by choosing a batch size of 128, which sets how many training samples are processed together in each step. The training images and labels are then converted from NumPy arrays into a TensorFlow dataset using a function that creates slices from the tensors. This dataset is shuffled with a buffer of 6,000 elements and a fixed seed, so the order is mixed while remaining reproducible, which helps prevent the model from relying on the original data order. Finally, the shuffled data is grouped into batches of the chosen size, which helps control memory use and improves training efficiency, especially for large datasets or complex models. We define a simple convolutional neural network for the MNIST digit images by first setting the input shape to 28 by 28 by 1. The model begins with a two-dimensional convolutional layer that has 16 filters, a kernel size of 3, and uses the ReLU activation to introduce nonlinearity, followed by a max pooling layer to reduce the spatial size of the feature maps. The output is then flattened so it can be passed to fully connected layers, starting with a dense layer of 32 units with ReLU activation to further process the features. Finally, an output dense layer with 10 units and a softmax activation produces class probabilities for the 10-digit classes, and the function returns this constructed model. Within the distribution strategy scope, we build the model using the previously defined function so it can train efficiently across multiple devices. We then compile the model with the Atom optimizer using a learning rate of 0.001, which works well for large and complex models. The loss function is set to sparse categorical cross-entropy, appropriate for multi-class classification tasks such as MNIST. Finally, we track accuracy as a metric to monitor how well the model performs during training. This code prints the total number of parameters in the model by calling a built-in method that counts them. The result gives a quick summary of how large and complex the model is. Knowing this number helps you understand the model's capacity and estimate its computational requirements. The model is trained on the dataset for 2 full passes, or epochs. During this process, the training runs in a silent mode, so it does not print detailed progress or intermediate results. This reduces clutter in the console and makes it easier to concentrate on the final training outcomes rather than on verbose logs. The code reads the final loss and accuracy values from the training history, which stores lists of these metrics for each epoch. By using negative indexing, it selects the last entry in each list, giving the loss and accuracy after the final epoch. These final values are then used to evaluate how well the model performed at the end of training. This code reports the model's performance at the end of training by printing the final loss and accuracy. It rounds each value to 4 decimal places, converts them to standard floating point numbers, and labels them clearly as final loss and final accuracy. This gives a concise, easy-to-read summary of how well the model trained. The code computes the effective global batch size by multiplying the batch size by the number of synchronized replicas provided by the training strategy. This shows how the batch size increases as more devices are used during training. It then prints this effective global batch size so you can see how the workload is distributed across all available devices. The code prints how many trainable variables the model has to verify that the chosen distribution strategy is working properly. Whether using mirrored strategy or default strategy, the goal is to keep all model variables synchronized across replicas. By checking the count of trainable variables, we confirm that the strategy maintains consistent parameters during training. This script shows how to use TensorFlow's MirroredStrategy for distributed training across multiple GPUs, It first sets a fixed random seed for reproducibility, checks how many GPUs are available, and either uses mirrored strategy for multiple devices or a single device strategy if only one is found. The code then loads and normalizes a subset of the MNIST dataset, defines a simple convolutional neural network within the strategy's scope, and trains it for 2 epochs. After training, it reports the final loss and accuracy, computes the effective global batch size as the batch size times the number of replicas, and confirms that the strategy keeps model variables synchronized across all devices. MultiWorker Mirrored Strategy. MultiWorker Mirrored Strategy is a way to scale synchronous data parallel training from a single machine to a cluster when one host, even with multiple GPUs, is not enough. Each worker machine holds a copy of the model and processes a different slice of the overall data batch. After every training step, the workers combine their gradients so the model weights stay synchronized across all machines. This strategy is well suited for training large models or handling very large datasets that exceed the capacity of a single host. MultiWorker Mirrored Strategy is designed for clusters of machines connected by a fast network, such as GPU servers in a data center or cloud. It lets you train large models like computer vision or recommendation systems by spreading the work across multiple GPU nodes or workers. This reduces training time, while the strategy handles coordinating workers and synchronizing gradients. As a result, the overall training process stays similar to training on a single machine, but scales to much larger workloads and tighter deadlines. In multi-worker mirrored strategy, all workers train in sync, so the global batch size is the sum of each worker's batch size. Adding more workers increases this global batch size, which can improve hardware utilization, but may require adjusting the learning rate or other settings to maintain good convergence. Because gradients must be shared at every step, this approach depends on fast, reliable, and uniform network connections. When these conditions are met, it scales training effectively across clusters and is well suited for very large tasks that exceed the capacity of a single machine, such as large language models or complex video analysis. Python code, MultiWorker Mirrored Strategy. This script gives a brief introduction to the basics of multi-worker mirrored strategy. It demonstrates how to simulate a multi-worker training setup using only a single machine. The example keeps the training process very small and the output extremely compact, so you can focus on understanding the core idea of the strategy without extra complexity. The commented line recommends installing TensorFlow version 2.20.0 to match the code being used. Specifying this exact version helps avoid problems that can occur when different versions change features or syntax. In general, locking in a library version is a common way to prevent unexpected behavior after updates. This keeps your environment stable and your code more reliable. We begin by importing 3 key Python libraries. The operating system library lets us interact with the system, for example, by setting environment variables. The JSON library allows us to work with JSON data, which is useful for configuration and data exchange. Finally, the random library provides tools for generating random numbers, often used for tasks like setting seeds to make experiments reproducible. We begin by importing TensorFlow, since it is the main library we use to build and train machine learning models. Right after importing, we check which version of TensorFlow is installed. This matters because different versions can change features or behavior. Confirming the version helps ensure that our code is compatible and will run as expected. To make sure our code gives the same results every time it runs, we use deterministic seeds. We first set the seed in the random library to the value 7 so that any random operations it performs are repeatable. We also set the environment variable that controls Python's hash behavior to 7, which makes hash-based operations consistent across runs. Together, these steps help ensure fully reproducible behavior in our program. We set TensorFlow's random seed to a fixed value, such as 7, so that any random operations it performs give the same results every time the code runs. This makes the behavior of the model predictable and repeatable. Such reproducibility is important for running experiments consistently and for debugging issues reliably. This line of code displays the version of TensorFlow that is currently in use. It provides a quick check that the correct version is installed. Confirming the version helps ensure that the rest of the code will run properly and remain compatible with the installed TensorFlow library. This code prints a message to show that it is simulating 2 workers running on a single process. It is part of setting up a distributed training environment using TensorFlow's MultiWorkerMirroredStrategy. This strategy enables parallel training across multiple devices or processes. In this example, everything runs locally on one machine to demonstrate the idea without requiring multiple physical machines. We begin by defining a simple JSON cluster specification, which is just a dictionary describing the configuration for our distributed training setup. In this example, we specify a single worker node running locally on a specific port. This allows us to simulate a multi-worker environment on one machine. Such a setup is useful for testing distributed training strategies without needing multiple physical machines. We configure TensorFlow distributed training by setting the tf.config environment variable to a JSON string that describes the cluster. In this example, the cluster has a single worker node running on the local machine at port 12,345. We also specify that the task type is worker and its index is 0, meaning it is the first worker in the cluster. This setup tells TensorFlow how the cluster is organized, so it can correctly distribute the workload. We use TensorFlow's MultiWorkerMirroredStrategy to distribute training across multiple workers so the model can train in parallel. This strategy lets the model run on several devices, such as multiple GPUs, and keeps their updates synchronized. By doing this, we can scale training efficiently, which is especially important for large datasets or complex model architectures. This line reports how many replicas are synchronized under the current distributed training strategy. The strategy object is a TensorFlow MultiWorkerMirroredStrategy that coordinates training across multiple devices. By checking its number of replicas in sync attribute, you can see how many replicas are actively involved in the synchronized training. This helps verify that the distributed strategy is configured correctly and working as intended, especially in a simulated multi-worker setup. We begin by creating a small synthetic dataset for training a model. Using TensorFlow's random normal function, we generate random feature values arranged in a matrix with 64 rows and 4 columns. This means we have 64 samples, each described by 4 features. Such a dataset is useful for simulating a simple, controlled training scenario without relying on real-world data. We generate classification labels by drawing random integers from a uniform distribution, so each possible label is equally likely. The result is a one-dimensional array with 64 elements. Each element is an integer from 0 to 2, representing 3 possible classes. The data type is set to integer, so these labels are appropriate for use in classification tasks. We begin by building a dataset from our features and labels using TensorFlow's data tools. Each feature vector is paired with its matching label, essentially zipping inputs and outputs together. This structure is crucial for training because it lets the model learn how inputs relate to the correct outputs. Using TensorFlow's dataset interface, also makes the data easy to manage later for operations like batching and shuffling. The dataset is first shuffled to mix the examples in a random order, which helps reduce bias during training. A shuffle buffer of 64 items is used, and a fixed random seed of 7 ensures the same shuffle order each time the code runs. After shuffling, the data is grouped into batches of 8 examples. These batches are processed together during training to make computation more efficient and the learning process more stable. The code uses the distribution strategy to split the dataset across multiple replicas or workers, so each one processes only part of the data. By dividing and managing the data this way, the workers can run in parallel. This parallel processing balances the workload across devices and is essential for efficient training in a distributed setup, improving both performance and scalability. We define a function that builds a simple neural network using the Keras sequential interface in TensorFlow. The network takes input data with 4 features, then passes it through a dense layer with 8 neurons that use the ReLU activation to add nonlinearity. It then outputs to a final dense layer with 3 neurons that use the softmax activation to produce class probabilities for 3 possible categories. The function returns this model so it is ready to be compiled and trained. Within the strategy scope, we first build a simple sequential model, so its variables are created in a way that supports distributed training. Pause. We then configure the optimizer using the Atom method with a learning rate of 0.01 to perform efficient gradient descent. Pause. Next, we define the loss function as sparse categorical cross-entropy, which is appropriate for multi-class classification problems. Pause. We set the reduction to none so that the loss is computed for each example separately, which is important for distributed training setups. This function computes the loss for each replica during distributed training by first calculating the loss for every example using sparse categorical cross-entropy, which measures how well the model's predictions match the true labels. It then averages these individual losses over the batch of 64 examples. This averaging uses TensorFlow's built-in method for computing average loss so that the loss is scaled correctly across multiple replicas. As a result, the loss calculation remains consistent and comparable across different distributed training setups. We define a distributed training step using TensorFlow's function decorator to make execution more efficient. Inside this step, a replica function runs on each device, where it unpacks the inputs into features and labels. Using a gradient tape, it passes the features through the model in training mode, computes the loss with a predefined loss function, and then calculates gradients of this loss with respect to the model's trainable variables. These gradients are applied with the optimizer to update the model's weights, and the replica function returns the loss value. The code uses a distribution strategy to run the replica step function on all available replicas at once, feeding each one its portion of the input data. This produces a separate loss value on each replica. The strategy then applies its reduce operation to combine these individual losses into a single scalar loss. It does this by summing the losses across replicas, giving one total loss for the entire batch. This reduction step is essential for synchronizing the results from all replicas into one coherent output. We run a simple training loop for 2 epochs to show the process. At the start of each epoch, we reset the total loss and batch counter. For every batch in the distributed dataset, we call the distributed training step. Get the loss for that batch, convert it to a regular number, and add it to the running total while increasing the batch count. After all batches are processed, we compute the average loss by dividing the total loss by the number of batches. We then report the epoch number and this average loss, rounded to 4 decimal places. To quickly check how well the model is working, we take a small subset of our feature data, such as the first 8 samples. We then use this limited batch to generate predictions and review the results. This brief evaluation lets us inspect the model's behavior on a manageable number of examples without running a full, time-consuming assessment. We now use the trained model to make predictions on a small batch of data, taking the first 8 feature samples. By turning off the training setting, we put the model into inference mode so it does not update its weights during this step. This allows us to evaluate how well the model has learned to classify the data based on its previous training. This code prints the predicted class for each input sample produced by the model. It uses a TensorFlow function to find the position of the largest value in the output for each sample, which represents the chosen class. The result is then converted to a NumPy array, so it is easier to inspect. Finally, these predicted class indices are printed to the console to quickly check the model's behavior after training. This script shows a simple example of distributed training in TensorFlow using a MultiWorkerMirroredStrategy simulated on a single machine. It sets deterministic seeds, checks the TensorFlow version, and builds a small synthetic dataset of features and labels that is distributed across the worker. A basic neural network with 2 dense layers is trained for 2 epochs using the atom optimizer and sparse categorical cross-entropy loss, while reporting the average loss for each epoch. Finally, the script evaluates the model on a small batch and prints the predicted class indices, along with key outputs such as the TensorFlow version and the number of replicas running in sync. TPU strategy basics. The TPU strategy in TensorFlow is designed to efficiently train large models and datasets by taking advantage of tensor processing units. It works as a data parallel approach that is tightly integrated with TPU hardware, which differs from CPUs and GPUs. TensorFlow automatically replicates the model across TPU cores, splits the input data for each core, and coordinates forward and backward passes while aggregating gradients. This allows training tasks like large language models or high-resolution image classification to scale better than on a single GPU, while hiding most of the low-level device and communication complexity from the user. TPU strategy is mainly used in cloud environments, where pre-configured notebooks or jobs handle the connection to the TPU cluster and map your computation automatically. It is especially valuable for large, parallel experiments, such as tuning complex models or training multilingual systems. Because TPUs are optimized for dense linear algebra, models that rely heavily on these operations gain the most benefit. The strategy also works smoothly with Keras, so many existing models can run on TPUs with only minimal changes. TPU strategy is best when you need very high throughput and stable performance at large scale, as long as your model and inputs match TPU hardware constraints. You should use larger batch sizes and choose data types and shapes that are efficient for TPU operations to fully utilize the cores. This makes TPUs well-suited for large recommendation systems, pre-training language models on massive text, and research on complex architectures that are too heavy for a single GPU. The strategy also manages replicas, batching, and gradient updates for you, so you can focus mainly on designing and improving the model itself. Python code TPU strategy basics. This script gives a simple introduction to using a basic TPU distribution strategy. It is designed to run safely even if you do not have access to real TPU hardware. The goal is to focus on the core concepts rather than performance details. To do this, it demonstrates the ideas with a very small example built using Keras. The line that begins with an exclamation mark is a shell command used to install TensorFlow version 2.20.0. It is typically run in a Jupyter notebook or similar environment. The purpose is to make sure that this exact TensorFlow version is available before running the rest of the script. This helps ensure that the code is compatible with the installed library, especially when features differ between TensorFlow versions. We begin by importing 3 key libraries. The operating system library lets us interact with the system environment. The random library allows us to generate random numbers, which is helpful for setting seeds and making results reproducible. Finally, we use the numerical computing library NumPy to work efficiently with arrays and perform mathematical operations. To make our code produce the same results every time it runs, we set deterministic seeds for the random number generators. We first set the seed in the random library to a fixed value, such as 7, so its random operations become repeatable. We then set the seed in the NumPy random module to the same value, ensuring that NumPy's random outputs are also reproducible. This consistency is important for debugging and for reliably verifying experimental results. We begin by importing TensorFlow, a powerful library used to build and train machine learning models, especially for deep learning. We then import the Keras tools that come with TensorFlow. Keras provides a high-level interface that simplifies creating neural networks, so we can design and experiment with models more quickly and easily. This line of code prints the version of TensorFlow that is currently in use. It reads the version information stored inside the TensorFlow library and displays it. Knowing the exact version helps you check compatibility with other tools and can be important when diagnosing problems. In practice, it is a quick way to confirm that your environment is set up as expected. This code tries to use a TPU, a specialized processor for speeding up machine learning. It first looks for available TPU resources, connects to the TPU cluster, and initializes the TPU system so it is ready for computation. If this setup works, it creates a TPU strategy for distributed training and marks the device type as TPU. If any step fails, it falls back to a default strategy on CPU or GPU and updates the device type accordingly, so the program can still run on whatever hardware is available. This line of code prints the distribution strategy that TensorFlow is using by checking the type of the strategy object and reading its name. It also prints the device type that was identified earlier in the script. Together, this tells you whether the code is running on a TPU, CPU, or GPU. This information is important for confirming that the environment is set up correctly and that the model is using the intended hardware for training. We begin by loading a small part of the MNIST dataset using Keras. MNIST is a standard dataset of handwritten digit images used to train and test image processing models. In this step, we load only the training portion, which contains the images and their labels. Using just this subset lets us train our model more quickly and with fewer computational resources while still demonstrating the core ideas. The code uses only the first 2048 training images and their labels, creating a smaller subset of the original data. This reduced dataset makes the training and testing process faster. It is especially useful for quick experiments or demonstrations where full-scale training would take too long. To prepare image data for a neural network, the pixel values are first converted to floating point numbers between 0 and 1 by dividing each value by 255, which helps the model train more effectively. Then, an extra dimension is added to the data to represent the image channels, turning each image from a two-dimensional array into a three-dimensional one. This added channel dimension is required because convolutional layers expect input data to include a channel, even when working with single-channel grayscale images. Before building the model, the code prints the shapes of the training data and labels to confirm they are correctly formatted. This check verifies that the dimensions of the inputs and outputs match what the model expects. By doing this early, it helps detect and fix formatting or alignment problems before training begins. We define a function that builds a Keras sequential model given an input shape and a number of classes. It starts with a two-dimensional convolutional layer with 16 filters of size 3 by 3 and a ReLU activation, followed by a flattening step to feed into fully connected layers. Then it adds a dense layer with 32 units and ReLU, and a final dense layer with as many units as there are classes, using softmax to produce class probabilities. The model is compiled with the Atom optimizer, sparse categorical cross-entropy loss for multi-class problems with integer labels, and accuracy as the evaluation metric. And the function returns this compiled model ready for training. We set the global batch size to 128, meaning the model processes that many samples before updating its weights, which is important for efficient training on distributed hardware like TPUs. We also choose to train for 2 epochs, so the model passes through the entire training dataset twice. This small number of epochs is used for quick experimentation, allowing us to see results without long training times. Within the distribution strategy scope, we build and train the model so it can run across available devices like GPUs or TPUs. We call a model creation function with the training data shape and number of classes, which returns a sequential model. This model includes convolution, flattening, and dense layers, and is compiled with the Atom optimizer and sparse categorical cross-entropy loss. Together, this setup enables efficient training that follows the chosen distribution strategy. The model is trained using a fit function that takes the training data and their labels as input. It uses a specified batch size, so the data are processed in smaller chunks rather than all at once. The number of epochs controls how many times the model goes through the entire dataset during training. The verbosity setting is turned off, so the training runs without printing detailed progress messages. At the end of training, we look at the last recorded loss value to see the model's most recent error, and we check the last recorded accuracy value to see how well it performed on the training data. These final values summarize the model's learning progress and overall performance. By examining them, we can quickly judge how effectively the model has learned from the data. The code reports the model's final performance after training by printing the last recorded loss and accuracy values. It converts each of these values to a floating point number and rounds them to 4 decimal places to make them easier to read. The final loss summarizes how well the model minimized error, while the final accuracy shows how often it correctly predicted the training labels. Together, these two numbers provide a quick overview of how effective the model was during training. This code reports how many replicas the current distribution strategy is using. In other words, it tells you how many copies of the model are being trained in parallel. Knowing this helps you understand how the workload is spread across the available hardware, and how that might affect performance and training speed. The strategy object exposes this through its attribute that gives the number of replicas in sync. This script shows how to use a basic tensor processing unit distribution strategy in TensorFlow. It first tries to detect and initialize a TPU, and if none is found, it falls back to a CPU or GPU. Using a small, normalized subset of the MNIST dataset, it defines and compiles a simple convolutional neural network within the distribution strategy. The model is trained for a short run with minimal logging, and afterward the script prints the final loss and accuracy to summarize performance. It also reports how many replicas were used for synchronized training, illustrating how many devices participated in parallel processing, and how TPU strategies can be applied even without actual TPU hardware. Data parallelism basics. TensorFlow replicas explained. In TensorFlow's distributed training, replicas are multiple copies of the same model running in parallel on different devices, all working together as one logical model. Each replica performs the same computations, but on different parts of the input data, such as images from different sources. They share the same model parameters, so their combined work contributes to a single learning process. This design lets TensorFlow scale the same training task from one GPU to many GPUs, or even across multiple machines. In TensorFlow's distribution framework, multiple replicas work together as one coordinated model rather than as separate models. Each replica runs the same training steps, including making predictions, computing loss, and calculating gradients. TensorFlow automatically manages creating these replicas, assigning them to devices, and distributing the data, so you do not have to control each device manually. Because the replicas are synchronized, training progresses as if a single model were learning from a larger batch of data. In TensorFlow, replicas let you scale training by separating local and global views of the work. Each replica locally processes its own mini-batch and computes gradients as if it were training alone. Globally, all replicas synchronize their results to mimic training with a larger batch on a single device, which improves speed and hardware use. This setup lets you focus on defining one model and one training step, while TensorFlow manages the coordinated execution across replicas for efficient data parallelism. Python code, TensorFlow replicas, explained. This script gives a conceptual explanation of TensorFlow replicas using a very small example. It shows how MirroredStrategy creates multiple copies of a model across devices to achieve data parallelism. The focus is on how each replica processes different parts of the data in parallel and then synchronizes updates so the model stays consistent. Overall, it introduces the basic idea of distributed training with mirrored replicas and coordinated synchronization. The line with the exclamation mark is a command to install TensorFlow version 2.20.0. Using this exact version helps ensure the script runs correctly and avoids compatibility problems that can occur with other versions. This kind of command is usually executed in a Jupyter notebook or a similar environment that allows running shell commands directly. We begin by importing TensorFlow because it is the main library we use to build and train our machine learning models. It provides tools for creating neural networks, managing data, and running computations efficiently. TensorFlow can use different types of hardware, such as CPUs and GPUs, to speed up these operations. Having access to this functionality is essential for everything we will do in this script. We begin by setting a fixed random seed using TensorFlow's random utilities, so that any random operations it performs will give the same results every time the code runs. This makes the behavior of the program predictable and repeatable. Such reproducibility is especially important when debugging models or comparing results across different runs, because it ensures that differences in outcomes are due to real changes in the code or data. This line displays the version of TensorFlow that is currently in use. It provides a quick check that your environment is running the expected version of the library. Confirming the version helps ensure compatibility with your code and can be important when diagnosing issues or debugging. This code uses TensorFlow's configuration tools to detect which logical GPUs are available on the system. By listing the logical devices of type GPU, it reveals how many GPU resources can be used for computation. This information is important for planning and setting up data parallelism strategies, since it shows what hardware is available for distributing TensorFlow workloads. To decide how many devices the strategy will use, We first check how many logical GPUs are available. We then apply a maximum operation so that even if no GPUs are found, we still count at least one device. In that case, the single device is typically the CPU. This approach guarantees the strategy can always run with at least one device, making it flexible and robust across different hardware setups. The code prints how many devices will host the replicas, which tells us how many processors are available for parallel work. This number is important because it shows how the workload can be distributed across multiple GPUs or CPUs. By knowing the device count, we can understand how data and computations will be split and confirm that the strategy can manage the replicas efficiently. We use TensorFlow's MirroredStrategy to enable data parallelism across multiple devices, such as GPUs. This strategy automatically splits the training data, so each device, or replica, processes a portion in parallel. It then synchronizes and aggregates the results from all replicas. By doing this, it helps scale training on large datasets and makes more efficient use of available hardware resources. This line reports how many replicas the MirroredStrategy will manage. In TensorFlow, a replica is a copy of the model that runs on its own device, such as a separate graphics processor. The strategy object automatically figures out how many replicas it can synchronize based on the hardware it detects. Knowing this number helps you understand how the workload is split across devices, which is important for tuning performance in data parallel training. We set the global batch size by multiplying 8 by the number of synchronized replicas in the strategy. This makes the batch size grow with the number of devices used. As a result, each replica handles an equal share of the data during training. This approach keeps data parallelism efficient across all available devices. We construct a small synthetic dataset to use in our demonstration. To do this, we generate a sequence of floating point numbers starting at 0 and continuing up to the global batch size. These numbers act as simple feature values. This synthetic data then serves as input features for our model training examples. In this example, we create labels for our dataset by simply doubling each feature value. So every label is 2 times its corresponding feature. This gives us a very direct linear relationship between features and labels. Such a setup is useful for a basic regression task because it keeps the target behavior simple and predictable. That way, we can concentrate on understanding how data is distributed and how the model is trained across different replicas, without being distracted by a complex labeling scheme. We check that the shapes of the features and labels match to avoid unexpected broadcasting problems during computations. When shapes do not align, element-wise operations can behave incorrectly or fail. This mismatch can also cause issues when feeding data into models. Ensuring identical shapes helps prevent these errors and keeps the behavior of the operations predictable. We create a TensorFlow dataset from our feature and label tensors to prepare the data for the model. Using the TensorFlow dataset API lets us manage and process the data efficiently during training. This dataset will then be batched and distributed across multiple replicas, so the model can be trained in parallel. The code takes the dataset and splits it into batches based on the global batch size, so each batch contains that many samples. This batching step is important for efficient training because it lets the model process data in manageable chunks. It is especially crucial in distributed training, where it ensures that each replica receives and processes the same amount of data during training. The code uses the distribution strategy to automatically split the dataset across all available replicas. Each replica receives and processes its own portion of the data in parallel. This setup enables data parallelism, where the same model is trained on different subsets of the data at the same time. As a result, training becomes more efficient and can run significantly faster. Within the strategy scope, we build a very simple linear model so that all its variables are created on the devices controlled by the strategy and can be synchronized across replicas. We use a sequential model from TensorFlow Keras, which lets us stack layers in order. The model takes a single input feature and passes it to one dense layer with a single unit, which is typical for linear regression with one output value. This minimal design focuses on illustrating how to distribute a model across multiple devices, rather than on model complexity. We define a mean squared error loss function using TensorFlow's built-in tools to measure how well a regression model's predictions match the actual values. This loss is computed as the average of the squared differences between predicted and true outputs. By setting the reduction option to none, we tell TensorFlow to keep a separate loss value for each example, instead of automatically averaging over the whole batch. This gives us more flexibility to decide later how to combine or weight these individual losses during training. We use stochastic gradient descent as our optimizer with a learning rate of 0.1. During training, this optimizer updates the model's weights to reduce the loss function. Using a relatively small learning rate keeps these updates gradual, which helps the training process converge more smoothly and stably. We define a loss function for each replica that is scaled by the global batch size. First, we compute the mean squared error loss for each individual example without reducing it. Then we use TensorFlow's compute average loss function to scale this per example loss by the global batch size. This process ensures that the final loss value is correctly adjusted for the total number of examples processed across all replicas. We define a training step function, optimized using TensorFlow's function decorator to run efficiently on the hardware. This function performs a single training step on each replica in a distributed setup. It takes the distributed inputs and unpacks them into features and labels for each replica. This way, every replica processes its own portion of the data during training. Inside the replica step function, the input tensors are first reshaped to have a single column, so they match the model's expected input format. The model then performs a forward pass under a gradient tape, which records the operations needed to compute gradients. A loss value is calculated by comparing the model's predictions with the true labels using a chosen loss function. Gradients of this loss, with respect to the model's trainable variables, are then computed and applied to update the model's weights, keeping all replicas synchronized. Finally, the function returns the loss value for that replica. The code uses a distribution strategy to run the replica step function on all replicas at the same time. It does this by calling the strategy's run method with the replica step function and the distributed features and labels. As a result, each replica handles its own portion of the data in parallel. This parallel execution enables more efficient computation across multiple replicas. The code combines the loss values from all replicas into one overall scalar loss. It does this by calling the strategy's reduce method, which aggregates the per-replica losses. The reduction is set to sum, so it adds the losses from each replica together. This produces a single mean loss value that represents the total loss across the distributed computation. This code returns the mean loss value that has been synchronized across all replicas in a distributed training setup. In other words, it computes the average loss from all devices involved in the training step. Using this shared value ensures that the model's performance is evaluated consistently across the entire distributed system. We take a single batch from the distributed dataset and use it to run one synchronized training step across all replicas. This distributed step produces an initial loss value, which we convert to a standard floating point number for easier interpretation. After this single update, we stop the loop. since the goal is only to observe and report the initial loss after one coordinated training step. We print the loss value after completing one synchronized training step across all replicas. This shows how well the model is doing after a single update. It provides a quick check that the distributed training is working as expected. If the loss looks reasonable, we know the process is functioning correctly. We can see that the model's parameters are shared by looking at the current weight in its first layer. To do this, we read the kernel value from the first neuron in the dense layer and convert it to a standard floating point number for easy interpretation. This single weight value is the same across all replicas, which shows that the model's parameters stay synchronized during distributed training. The code prints the value of a shared model weight after it has been updated during distributed training. This weight is common to all replicas, so its value reflects the synchronized state of the model across devices. By rounding it to 4 decimal places, the output gives a clear and compact view of this parameter. This helps you see how the training process is changing the model's shared weights in a distributed environment. This script shows how TensorFlow's mirrored strategy performs data parallelism across multiple GPUs using a simple linear model. It sets a random seed, detects available devices, and creates a synthetic dataset where labels are twice the input features, then distributes this data across all replicas. Inside the strategy scope, it defines a basic linear model trained with mean squared error and a stochastic gradient descent optimizer, using a custom loss function that scales by the global batch size. A distributed training step runs on each replica, reshaping inputs, making predictions, computing gradients, and updating shared model weights. After one training step, the script prints the loss and the common model weight to illustrate how parameters stay synchronized across devices in this multi-GPU setup. All reduce gradients. All reduce is crucial in data parallel training because it makes many replicas behave like a single model update. Each replica processes a different part of the batch and computes its own gradients, which would cause the models to drift apart if applied independently. Instead, all reduce collects and combines these gradients, then sends the aggregated result back to every replica. This ensures all replicas apply the same gradient update and keep their model weights synchronized after each training step. All reduce operations combine gradient values from all devices, usually by summing or averaging them, and then share the result back to every replica. These gradients are computed separately on each device, and specialized algorithms, such as ring-based or tree-based schemes, manage this communication efficiently. Although deep learning frameworks hide most of these details, the chosen algorithm can strongly affect performance, especially with large models or many accelerators. In multi-GPU training, an efficient all-reduce reduces communication delays and ensures every replica receives the same globally reduced gradient, which is essential for consistent model updates across all devices. Using all-reduce for gradients in distributed training makes multiple replicas behave like a single model trained with a larger batch size. Each replica processes different data, then all-reduce combines their gradients, so every replica applies the same update and keeps identical weights. This shared update helps the model converge stably and lets it learn from the full batch at once. It is commonly used when training language models on many GPUs or recommendation systems across several machines, and provides a clear, unified view of the training dynamics. Python code, all reduce gradients. This script demonstrates how gradients are combined when using an all-reduce operation in distributed training. It applies TensorFlow's mirrored strategy on simple data to show how multiple replicas work together. The key idea is that gradients from each replica are synchronized and averaged before updating the model. This highlights the behavior of gradient aggregation across replicas in a distributed setting. The commented line is instructing you to install TensorFlow version 2.20.0. This ensures that the script uses that exact version, which may be required for compatibility. By fixing the version, it helps prevent errors or unexpected behavior caused by differences between TensorFlow releases. In short, it is there so the code runs reliably without version-related issues. We begin by importing TensorFlow to build and train machine learning models. We also import NumPy to handle large multidimensional arrays and perform mathematical operations on them. In addition, we bring in the operating system module so the script can work with environment settings and file paths. Together, these imports provide the core tools needed for efficient data handling and distributed training in the script. To make code results repeatable in TensorFlow, we enable deterministic operations by adjusting the environment settings. This ensures that running the same code multiple times produces consistent outputs, which is important for debugging and comparing experiments. We also set a fixed random seed in NumPy so that any random numbers it generates are the same each time. In addition, we set a seed for TensorFlow's own random number generator, so its random operations are also reproducible across runs. This line of code prints the version of TensorFlow that is currently in use. It provides a quick check that the library is installed correctly. Confirming the version helps ensure it matches what the rest of the code expects. This reduces the risk of compatibility issues when running your program. We begin by creating a mirrored strategy, which enables data parallel training across multiple devices by keeping copies of the model's variables on each device. This strategy coordinates and synchronizes the training process so that all devices update their variables consistently. After setting it up, we print how many replicas are in sync, which tells us how many devices are actively participating in parallel training. This confirms that all replicas are working together efficiently during training. We define the global batch size as 4. Meaning 4 samples are processed in each training step across all replicas. To distribute the work evenly, we divide this global batch size by the number of replicas that train in sync. The result is the per-replica batch size, which tells us how many samples each replica handles. This setup ensures that every replica processes an equal share of the data and supports efficient parallel training. We create a simple synthetic dataset using TensorFlow constants, where the features are the numbers 1 through 4, each formatted as a small list to match the model's expected input shape. The labels are defined as twice each feature value, forming a basic linear relationship between inputs and outputs. This artificial setup provides a clean, controlled example for training a model, so we can focus on understanding the mechanics of distributed training without dealing with the complexity of real-world data. Before building the dataset, the code first checks that the number of feature samples matches the number of label samples, so that every feature has a corresponding label for training. It also confirms that the number of feature samples equals the global batch size. Together, these checks ensure the dataset is consistent and correctly sized for the intended batch processing. We begin by turning our features and labels into a TensorFlow dataset using a function that creates paired slices from both. Then we group this dataset into batches using the global batch size and set it to drop any incomplete batch at the end. This means that if the total number of samples is not an exact multiple of the batch size, the extra samples are ignored. This batching setup prepares the data for efficient processing during model training. This code uses a mirrored strategy to distribute the dataset across multiple replicas of the model. Each replica receives a portion of the data, which enables parallel training while keeping the overall process synchronized. The experimental dataset distribution method prepares and feeds data to each replica, ensuring that the workload is evenly split and efficiently managed across all available devices. Inside the strategy scope, we build a simple linear model using the Keras sequential API, which lets us stack layers in a straight line. The model has a single dense layer that represents a linear relationship between input and output, often described as an output equal to a weight times the input plus a bias. This dense layer has one unit, so it produces a single output value and includes a bias term. The input shape is set to 1, meaning each example has a single input feature. This configuration is a standard setup for linear regression, where the goal is to learn how input features relate to output labels. We use the mean squared error loss from TensorFlow, which measures how far predictions are from the true values by averaging the squared differences between them. By configuring it so that the reduction is set to none, the loss is kept separate for each individual example, instead of being combined into a single value. This lets us manually process or aggregate the per-example losses later in whatever way we need. We use a simple stochastic gradient descent optimizer with a learning rate of 0.1 to train the model. During training, this optimizer updates the model's weights to reduce the loss function. Stochastic gradient descent is chosen because it is straightforward and efficient, especially when working with large datasets. These properties make it well-suited for our distributed training setup. This function computes the loss for each training example using a mean squared error loss object, then combines those values into a single loss for the whole batch. It does this by averaging the individual losses across the global batch size. The averaging uses TensorFlow's compute average loss utility, which correctly scales the loss during distributed training. As a result, the reported loss remains consistent even when the number of replicas changes. This function performs one training step across all replicas and is wrapped with TensorFlow's optimization decorator for faster execution. Inside the function, the distribution strategy's run method calls a replica step on each replica in parallel. It passes in distributed inputs and receives the losses and gradients computed on each replica. This design lets each replica handle its own portion of the data, while keeping gradient computation synchronized across all replicas. To report the mean loss across all replicas, we use the strategy's reduce method, which aggregates the individual losses by summing them. The reduction is defined as a sum, so it adds the loss from each replica together. With the axis set to apply across all dimensions, this produces a single scalar value. This value represents the synchronized mean loss across replicas and serves as a consistent metric for evaluation. This function returns two outputs: the mean loss and the gradients from each replica in a distributed setup. The mean loss is computed by averaging the individual losses across all replicas so that it reflects the overall performance of the system. The gradients have already been synchronized across replicas by the optimizer's gradient application step, so they can be returned directly. This design ensures that both the reported loss and the gradients are consistent and ready for further processing or analysis. The replica step function starts by splitting the input into features and labels for each replica. It then uses TensorFlow's gradient recording mechanism to track the operations needed for automatic differentiation. With training mode enabled, the model generates predictions from the features, and a predefined loss function compares these predictions to the true labels. This process sets up the gradients required to update the model's weights during training. Using TensorFlow's gradient tape, we compute how the loss changes with respect to each trainable parameter, which tells us how each parameter influences the loss. We then pass these gradients to the optimizer's method that applies gradient updates, adjusting the model's weights to reduce the loss. Finally, we return both the loss and the gradients so we can monitor the model's performance and understand the direction of the parameter updates. We iterate over the distributed dataset only once to capture a single batch of data. As soon as the first batch is obtained, we store it and immediately stop the loop, so no additional batches are taken. This single batch is then used to run one distributed training step. Doing this allows us to focus on testing how gradients are synchronized across replicas during that step. In a single distributed training step, we call a specialized function that returns the mean loss and the gradients from each replica. The mean loss summarizes how well the model performed during that step, averaged across all replicas. The gradients show how the model's parameters should be updated on each replica. This process keeps the training synchronized so that all replicas work together to update the model consistently. The code collects the kernel weight gradients from each replica in a distributed training setup. It uses the distribution strategy to access the local gradient results computed on each individual replica. This shows how gradients are gathered from all replicas and helps explain how they are distributed and synchronized during training. This code reports the mean loss after one synchronized training step across all replicas, giving a quick measure of how well the model is learning once all gradients have been averaged and applied. By converting this mean loss to a standard floating point number, the output becomes a simple, clean value. This makes the result easy to read, log, and interpret when monitoring training performance. The code loops through the gradients from each replica, and for each one, prints the replica's index and the corresponding kernel gradient value. It does this by converting the gradient tensor to a NumPy array and taking the first element, which represents the gradient for the kernel weight. This printed output is used to confirm that gradients are being computed and synchronized correctly across all replicas. The code prints the final shared kernel weight of the model to verify that distributed training worked correctly. It reads the model's first trainable variable, which is the kernel weight, converts it to a readable floating point value, and then outputs it. Because this weight is shared across all replicas, seeing the same value confirms that gradient averaging and synchronization has been successful. In other words, all replicas end up with an identical kernel weight after the distributed training step. This script shows how TensorFlow's mirrored strategy performs synchronized gradient averaging in a simple distributed training setup. It builds a basic linear model on a small synthetic dataset and trains it across multiple replicas so that gradients are averaged and applied in sync. When you run it, the script reports the TensorFlow version, the number of synchronized replicas, and the mean loss after one training step. It also displays the gradients from each replica and the shared kernel weight, confirming that model parameters stay synchronized across all replicas, which is essential for efficient data parallel training in distributed environments. Sync and async training. In distributed systems, synchronous training means all replicas process their portions of data at the same time, and then update the model together. This keeps the model weights identical across all replicas at every training step. However, the overall speed is limited by the slowest replica, because all replicas must wait at synchronization points before moving on. In asynchronous training, different replicas update shared model parameters independently, without waiting for each other. This improves hardware efficiency and overall throughput, especially when devices have different speeds or experience network delays, because no worker is forced to idle. The trade-off is that some replicas may use slightly outdated model weights, which adds noise to the optimization process and can slow convergence. Even so, Asynchronous training is often useful when flexibility and speed of processing are more important than perfectly synchronized updates. In modern deep learning, synchronous training is usually preferred for large-scale data parallelism on GPUs and TPUs because it is efficient and has predictable convergence. In this approach, devices coordinate to aggregate gradients and broadcast updates so they always share the same model state. Asynchronous training is more common when devices are loosely connected, such as across data centers or with mixed hardware, where strict synchronization is difficult. These systems often rely on parameter servers and careful learning rate schedules to keep training stable. Understanding both approaches helps you choose the right strategy for your environment's scale and performance needs. Adjusting code for distribution. Strategy scope basics. In TensorFlow, a distribution strategy scope is a special context where everything you create is prepared for distributed execution. Inside this scope, TensorFlow automatically handles where variables live and how computations run in parallel, while code outside the scope behaves normally. This lets you keep most of your code unchanged and clearly isolate the parts that must be aware of distribution, such as model construction and optimizer setup. Using the scope ensures that operations that depend on replica behavior are managed correctly. When preparing code for distributed training, it is important to control where you enter and exit the strategy scope and what you create inside it. You should define model architectures, layers, and trainable variables within the strategy scope, so their weights are correctly managed and synchronized across devices. For example, when building a convolutional neural network, you enter the strategy scope before creating the model and optimizer to ensure proper weight distribution. In contrast, local objects that do not need replication, such as configuration settings or logging tools, can be created outside the scope. Keeping this separation helps avoid problems like variables being placed on the wrong devices or failing to stay in sync across replicas. When using distribution strategies, remember that custom operations involving model variables or gradients must run inside the strategy scope. High-level APIs usually handle this for you, but if you write your own training loop, such as for a speech recognition system, the training step function needs to execute under the strategy, so replicas are managed correctly. The same applies to custom metrics or moving averages that depend on data from multiple replicas. Following this pattern helps your code scale efficiently from a single GPU to many devices or machines with minimal changes. Python code, strategy, scope, basics. This script demonstrates how to use strategy scopes when building models. It compares creating a model in a standard non-distributed way with creating one under a distributed training strategy. The main goal is to highlight exactly where you enter the strategy scope and where you exit it, so you can see how model creation changes between these two approaches. A commented line is a note telling you to install TensorFlow version 2.20 if it is not already on your system. This step prepares the environment so the rest of the script can run correctly. The comment is meant to guide users who have not set up TensorFlow yet. They can simply remove the comment mark and run the line to install the required version. We begin by importing TensorFlow, the main library we will use to build and train our machine learning models. TensorFlow provides a complete set of tools for creating deep learning applications. Throughout this script, it will handle the construction, training, and management of our neural networks. This code uses TensorFlow's random module to set a fixed global random seed. Doing so makes all TensorFlow operations that involve randomness produce the same results every time the program runs. This deterministic behavior is important because it allows experiments to be reproduced reliably. It also makes debugging easier, since you can consistently recreate the same conditions and outputs. This line displays the version of TensorFlow that is currently in use. It provides a quick way to check which release of the library is loaded in your environment. Knowing the exact version is important because different versions may change features or behavior. This helps you ensure compatibility and makes debugging easier when something does not work as expected. We define a function that builds a simple neural network model using the input shape and the number of output classes as parameters. Inside this function, we create a sequential model with two dense layers. The first layer has 16 units and uses the rel activation to introduce nonlinearity. The second layer has as many units as there are classes and uses the softmax activation to produce a probability distribution over those classes. This structure allows the model to learn from the input data and make classification predictions. The model is compiled using the Atom optimizer with a learning rate of 0.01, chosen for its efficiency with sparse gradients. It uses sparse categorical cross-entropy as the loss function, which is appropriate for multi-class classification when the labels are integers. The model is also configured to track accuracy as a performance metric during training and testing. After these settings are applied, the compiled model is ready to be trained. To quickly demonstrate how the model works, we first create a small dummy dataset. We choose 32 samples, meaning there are 32 data points. Each data point has 8 features, which define its dimensions. We also set the number of classes to 3, indicating the 3 categories the model will learn to predict. We begin by using TensorFlow to create random input features, drawing values from a normal distribution and arranging them in a tensor whose shape is set by the number of samples and features. This synthetic tensor acts as our model's input data. We then generate labels with another TensorFlow function that samples random integers from a uniform distribution, assigning each sample a class index from 0 up to 1 less than the total number of classes. These labels serve as the target outputs the model will try to learn during training. Before using the tensors, the code first checks that the feature and label shapes match the expected dimensions. This confirms that the features have the correct number of samples and feature values, and that the labels have the correct number of samples. These checks act as early safeguards, catching shape mismatches before they can cause errors during model training or evaluation. We begin by creating a simple model without using any distribution strategy. To do this, we call a model construction function and provide the input feature shape and the number of output classes. The model is built with TensorFlow's Keras sequential interface, which stacks layers in a straightforward, linear order. At this stage, all computation runs on a single device, with no parallel processing or distribution across multiple machines or accelerators. The code trains the plain model for a single epoch using the given features and labels. It uses a batch size of 8, so the data is processed in small groups of 8 samples at a time. The training output is silenced by setting the verbosity to 0, which keeps the console free of progress messages. This setup provides a quick, quiet training run that emphasizes the model's performance rather than detailed logging. The code evaluates the plain model on the given features and labels without printing any progress details. It then retrieves the loss and accuracy from this evaluation. The accuracy value is rounded to 4 decimal places for clarity and printed as the plain model's accuracy. This gives a concise summary of how well the model performs on the data. We use TensorFlow's MirroredStrategy to enable data parallelism, which means training the model across multiple devices, such as GPUs, at the same time. This strategy helps improve training speed and efficiency by splitting the workload. By setting it up, we prepare the environment for distributed training, so it can handle larger datasets and more complex models more effectively. Within the strategy scope provided by TensorFlow's MirroredStrategy, we create variables that are automatically distributed across multiple devices, which enables parallel training. Inside this context, we build the same simple model as before, so that all its variables are set up for distributed execution. Using the strategy scope ensures the model is correctly configured to take advantage of the distribution strategy's capabilities for training on multiple devices. The distributed model is trained on the same dataset as before by calling its training function with the input features and labels. It runs for a single epoch using a batch size of 8, and the training output is silenced by setting the verbosity to 0. This configuration lets the model learn from the data while taking advantage of the distribution strategy to perform the training in parallel. We now evaluate the distributed model using the same input features and labels as before. This evaluation runs silently, without printing any progress or results to the screen. During this step, the model's loss and accuracy on the given data are computed. These values are then stored for later analysis and comparison. We report the accuracy of the distributed model by rounding its value to 4 decimal places. This creates a clear, concise number that makes it easy to compare performance after training. By using this rounded accuracy, we can quickly assess how effective the distributed model is. The code prints the shape of the input features used by both models to verify that they receive data in the same format. This check confirms that the input structure is consistent between the non-distributed and distributed versions. As a result, any differences in their performance can be compared fairly, since they are based on identical input data. This script shows how to use TensorFlow's strategy scope to compare standard and distributed training of a simple neural network. It builds a small model with dense layers, compiles it with an atom optimizer and sparse categorical cross-entropy loss, and trains it on a dummy dataset of random features and integer labels. The model is first trained and evaluated on a single setup, then a mirrored strategy is applied to train an equivalent model across multiple devices for data parallelism. The script compares the accuracy of both runs and confirms they use the same input data shape, illustrating how easily TensorFlow can scale model training across devices using a distribution strategy. Distributed input pipelines. When moving from single device to distributed training, the main change is how you handle the input pipeline. In a single device setup, one dataset feeds the model, but in distributed training, that same dataset must serve multiple replicas across GPUs or machines. The distribution strategy automatically splits each global batch into smaller slices for each replica. To make this work correctly, build the dataset once, outside any replica-specific functions, and let the strategy manage how data is delivered to each worker. In distributed systems, you must clearly define how data is batched and consumed by each replica. The batch size you choose is a global size that is automatically divided among all replicas. So with 4 GPUs, a batch of 128 images means each GPU processes 32 images. To keep training consistent and efficient, you should prepare the dataset before entering the distributed environment, and apply operations like shuffling and caching at that stage. This approach helps avoid data inconsistencies and improves performance, especially for large datasets such as medical or satellite images. When training across multiple machines, each worker must read from the same dataset in a coordinated way so that no data is duplicated or skipped. Use input functions that support distributed reading, sharding, and file interleaving, so each worker gets a unique, consistent slice of the data. Avoid random or stateful operations inside replica-specific functions, since they can cause uncoordinated differences between workers. Instead, perform shuffling and data augmentation at the dataset level to keep behavior consistent. These practices help ensure stable, reproducible training especially in complex multi-center recommendation systems. Python code, distributed input pipelines. This script introduces the basics of distributed input pipelines. It compares how datasets are used in a standard non-distributed setup versus a distributed setup. The main emphasis is on how TensorFlow's distribution strategies work with datasets, and how batching behaves differently when training is distributed across multiple devices. The line that begins with an exclamation mark is a command to install TensorFlow version 2.20.0. Using this exact version helps ensure the script runs with the expected features and behavior. This is often important for compatibility with the code being demonstrated. Such a command is typically executed in a Jupyter notebook or a similar environment that allows direct use of shell commands. We start by importing 3 key Python libraries. The operating system library lets us work with the system, such as managing files and accessing environment settings. The random library provides tools for generating random numbers and performing random operations, which is useful for tasks like shuffling data. Finally, we import NumPy, a powerful numerical computing library that makes it efficient to work with arrays and perform mathematical calculations in Python. We start by importing TensorFlow, a powerful library used for machine learning and deep learning. This import gives us access to tools for building models, handling data, and taking advantage of hardware acceleration. After importing, we check which TensorFlow version is installed. Knowing the version is important because different versions can have different features or behaviors, and matching the version to our code helps avoid compatibility problems. We begin by setting a seed value, such as 42, so that any random operations in our code are reproducible. We apply this seed to the random library, to NumPy, and to TensorFlow so that all random numbers they generate stay consistent from one run to the next. This practice is especially important in machine learning because it ensures that experiments can be repeated and fairly compared across different runs. This command displays the version of TensorFlow currently in use. It provides a quick check that your environment is using the intended TensorFlow release. Confirming the version helps ensure that your code will run correctly and remain compatible with the rest of your project. The code uses TensorFlow to check which physical devices are GPUs and counts how many are available on the system. It does this by listing all GPU devices and measuring the length of that list. It then prints the number of detected GPUs. This information helps decide how to distribute computations across the available hardware. We create a simple synthetic dataset using a small set of 32 samples. The feature values are just the integers from 0 to 31, arranged as a column, so each value forms its own data point. The labels are generated by multiplying each feature value by 2 and converting the result to a floating point number. This produces a clean, linear relationship between features and labels, which is useful for illustrating basic machine learning ideas. This step takes the feature and label arrays from NumPy and converts them into a TensorFlow data dataset. Doing this lets us use TensorFlow's data pipeline tools, including efficient batching and shuffling. As a result, the data can be handled more effectively during training and fits smoothly into TensorFlow's overall workflow for scalable data processing. We set a global batch size of 8, meaning the dataset is processed in groups of 8 samples at a time. This small batch size is chosen mainly for demonstration, so it is easy to see how data is split and handled. It lets us compare how batching works in both non-distributed and distributed settings. Batch size is an important parameter because it affects how efficiently data is loaded and how the training process performs, especially in distributed systems. To build an efficient input pipeline, we first shuffle the dataset with a buffer size equal to the total number of samples, using a fixed seed to keep the process reproducible. We then group the data into batches based on the global batch size so the model can process multiple samples at once during training. Finally, we enable prefetching so that data is prepared in the background while the model is running. Together, these steps improve data handling and performance, especially for large datasets or distributed training setups. To check the shape of a batch in a non-distributed setting, we take a single batch from the training dataset and inspect it on one device. By printing the shape of the features in this batch, we see how the data is organized before any distribution strategy is used. This quick check helps confirm that the batching process is working correctly and that the data dimensions are as expected in a standard, non-distributed context. The code chooses a distribution strategy based on the available hardware. If it detects more than one graphics processor, it uses TensorFlow's MirroredStrategy to train the model synchronously across multiple devices by copying the model's variables. If there is only one graphics processor, or none at all, it falls back to a single device strategy on the CPU. This approach lets the same code run efficiently on different systems while taking advantage of parallel processing when possible. This code reports how many replicas are synchronized in the current distribution strategy. In other words, it tells you how many copies of the model are being trained in parallel. Knowing this helps you understand the training performance and how resources are being used. By checking the replica count, you can confirm that the distribution strategy is configured correctly and that the available hardware is being used efficiently. Within the strategy scope, we first create a shuffled version of the base dataset using a buffer that covers all samples and a fixed seed for reproducibility. We then batch the data using the previously defined global batch size and prefetch it to speed up the input pipeline with automatically tuned buffering. Finally, we pass this prepared dataset to the strategy's experimental distribute dataset method, which converts it into a distributed dataset suitable for running across multiple devices under the chosen distribution strategy. To inspect a distributed batch and see the shapes for each replica in TensorFlow, we first work around the fact that the distributed dataset does not support the take method. Instead, we convert the distributed dataset into an iterator and use its next method to manually retrieve a single batch. Within this batch, we apply a small helper function that returns the shape of its input tensor. By running this function on the batch, we can examine how the data is split and shaped across the different replicas. The code uses the strategy's run method to call a function on each replica that reports the shape of the data it holds and stores these results as the per-replica shapes. It then flattens the distributed batch to access one replica's data and uses that shape to infer the global batch size. Using this information, it prints the global batch shape, which reflects the full batch across all replicas. Finally, it prints the per-replica shapes to show how the overall batch is split among the different replicas. Within the distribution strategy scope, we build a simple sequential model in TensorFlow Keras with an input layer that takes a single feature and a dense layer with one unit to learn a linear transformation of that input. We then compile the model using stochastic gradient descent as the optimizer and mean squared error as the loss function. With this configuration, the model is prepared to train on the distributed dataset while taking advantage of the strategy for efficient computation. We briefly train the model to confirm that the input pipeline works correctly with the chosen distribution strategy. To do this, we call the model's training routine on the distributed dataset for a single epoch, so the model passes through the data once. We set the steps per epoch to 2, which divides the dataset into 2 parts for each pass. training output is turned off so nothing is printed, since the goal here is simply to verify that the distributed input pipeline and strategy are functioning as expected. This code reports the final loss from a short distributed training run. It looks up the loss values stored in the training history, then selects the last value in that sequence, which corresponds to the loss after the final training step. That value is converted to a floating point number for clarity. Finally, it is printed along with a brief message indicating that it represents the final loss from the distributed training process. This script introduces the basics of distributed input pipelines in TensorFlow. It sets a fixed random seed, checks the TensorFlow version and available GPUs, then creates a synthetic dataset with features and labels that is shuffled and batched. After showing how batch shapes look on a single device, it chooses an appropriate distribution strategy based on the number of GPUs and builds a distributed dataset to inspect per-replica batch shapes. Within this strategy, it defines and compiles a simple model, runs a brief training step, and prints the resulting loss. Overall, it demonstrates that the distributed input pipeline is working correctly across the available devices. Batch size semantics. When moving from training on a single device to using multiple devices, it is important to understand how batch size is defined. In distributed training, the global batch size is the total number of examples processed across all devices, while the per-replica batch size is the number each individual device handles. For example, if you use 4 GPUs with a global batch size of 128, each GPU processes 32 examples per step. This distinction affects how you set up your dataset and influences learning behavior, memory usage, and overall throughput as you change the number of devices. In distributed training, you set a global batch size that is shared across all devices, and the framework automatically splits this into smaller per-device batches. Each device processes its share of the data, but the model updates its parameters based on the combined results from the entire global batch. This is like several analysts each reviewing part of a dataset and then merging their findings into one overall report. If you add more devices without changing the global batch size, each device handles less data, but the overall batch and training behavior stay the same. This setup helps keep training dynamics consistent as you change the number of devices, as long as the global batch size matches your optimization goals. When you scale up distributed training by adding more devices and increasing the global batch size, performance does not automatically improve. Doubling devices and batch size changes how many examples are seen before each update, which can alter optimization. For large tasks, this may improve hardware use and speed, but you often need to adjust learning rates or regularization to keep model quality. For smaller datasets, very large batches can hurt generalization. The key is to balance device memory, throughput, and model behavior instead of increasing batch size without careful tuning. Python code, batch size semantics. This script provides a simple demonstration of how batch size works in distributed training. It clearly contrasts the global batch size, which is used across all devices, with the per-replica batch size used on each individual device. To do this, it applies a mirrored strategy and runs on a very small synthetic dataset, making the batch size behavior easy to observe and understand. The line with the exclamation mark is a command that installs TensorFlow version 2.20.0. Using this exact version makes sure the script runs with the expected features and behavior. It helps keep dependencies consistent and prevents problems that could occur if a different TensorFlow version were used. We begin by importing 3 key tools for our script. The operating system module lets us interact with the system, such as working with environment settings and files. NumPy provides efficient numerical computing and array manipulation. TensorFlow is then imported to build and train machine learning models. Together, these imports prepare the environment for handling data and running computations effectively. We first set an environment variable so that TensorFlow operations behave deterministically, which helps produce consistent results each time the program runs. We then set a random seed in NumPy to control its random number generation, and do the same in TensorFlow to control its own sources of randomness. Together, these steps make the behavior of the code repeatable across different executions. This reproducibility is especially important when debugging or comparing experimental results. This line of code displays the version of TensorFlow that is currently in use. It provides a quick check that your environment is running the version you expect. Confirming the TensorFlow version helps ensure that your code will be compatible with the installed library. This simple check can prevent issues caused by version mismatches. The code first checks which graphics processing units are available by calling a TensorFlow function that lists physical GPU devices. It then prints how many GPUs it finds, giving a quick overview of the system's GPU resources. Knowing this number is important for planning how to distribute computations efficiently across the available hardware. The code first checks how many physical GPUs are available. If at least one GPU is found, it uses a mirrored strategy, so training can be distributed and synchronized across all GPUs. If no GPUs are detected, it falls back to a single device strategy on the CPU. This approach lets the same code run on any machine by automatically choosing an appropriate training strategy based on the available hardware. The code reports how many replicas are synchronized by the chosen distribution strategy. This tells you how many copies of the model are training in parallel. That number determines how the global batch size is split across replicas. Knowing this helps you tune training so that the hardware is used efficiently. We set a small global batch size of 8, meaning that a total of 8 samples are processed together in each training iteration across all replicas. This value controls how many examples are handled at once by the entire distributed system. We then display this batch size to confirm the setting used in the demonstration. To set the batch size for each replica, we take the global batch size and divide it by the number of replicas that are running in sync. This gives a per-replica batch size that evenly distributes the workload across all replicas. We then print this value to verify it, which helps confirm how the data will be split and processed in parallel across multiple devices. We create a small synthetic dataset with 32 examples to illustrate a simple linear relationship. The feature values are a sequence of numbers from 0 to 31, arranged as a single column. Each label is computed by taking the feature value, multiplying it by 1/2, and then adding 1, with the result stored as a floating point number. This gives us a straightforward linear mapping from features to labels that is convenient for demonstration. Before building the TensorFlow dataset, the code first checks that the number of feature samples matches the number of label samples, so each feature has a corresponding label. It also confirms that both features and labels have only one column, meaning they are one-dimensional arrays. These validations help catch mismatches and shape problems early, preventing errors when the dataset is created. We begin by creating a TensorFlow dataset from the features and labels, so the data can be handled efficiently during training. We then group the data into batches using the global batch size, which is important for training the model in mini batches. Finally, we enable the option to drop any leftover data that does not fill a complete batch, so all batches have the same size and remain consistent throughout training. The code takes the base dataset and distributes it according to the selected strategy, such as MirroredStrategy or one-device strategy, based on the available hardware. This prepares the data for parallel processing so that multiple replicas can work at the same time. Each replica receives its own portion of the dataset for training. This step is essential for fully using the computational power of the devices, especially when multiple GPUs are available. Within the strategy scope, we define a simple TensorFlow Keras sequential model so that its variables are created on the correct devices. The model is built as a linear stack of layers, starting with an input that takes a single feature. We then add one dense layer with a single unit, which produces one output value. This minimal setup serves mainly to demonstrate how to create a model in a distributed strategy context. Within the strategy, we compile the model by setting its training configuration. We choose the stochastic gradient descent optimizer with a learning rate of 0.01 to update the model's weights and reduce the loss during training. The loss function is mean squared error, which measures the average squared difference between predictions and actual values. We also disable eager execution so the model runs in graph mode for better performance. The model is trained on the distributed dataset for a single epoch, meaning it passes through all the data once to update its weights. During this run, training is performed in silent mode, so no progress messages or detailed logs are shown. This setup is useful when you want quick training iterations without needing detailed feedback from the training process. We iterate over the distributed dataset only long enough to grab the first batch of features and labels. These are stored in variables that hold the data for each replica, allowing us to see how the batch is split across them. A break statement then stops the loop immediately, so we only capture and inspect this initial batch rather than processing the entire dataset. The code converts the per-replica tensors into simple lists so they are easier to inspect. It uses the distribution strategy to pull out the local feature tensors from each replica and collect them into a list of feature parts. It then does the same for the label tensors, creating a list of label parts. This makes it straightforward to see how both features and labels are distributed across the different replicas used by the strategy. The code first prints how many feature parts there are, which shows into how many segments the global batch is split across replicas. It then prints the shape of the first part to reveal the size of the data handled by a single replica. Finally, it prints the shape of the full global batch to confirm that the overall batch size is as intended. Together, these checks verify that the data is correctly divided and that each replica processes the expected amount of data. This line prints a small sample of the feature data from the first replica to check that the global batch has been correctly split into per-replica batches. It takes the first element of the first slice of the feature data and converts it into a NumPy array so it is easier to inspect. By examining this sample, you can verify that the data has been distributed across replicas as intended. This script shows how TensorFlow manages batch sizes when training across multiple devices. It sets up deterministic behavior, checks for available GPUs, and uses either a mirrored multi-GPU strategy or a single CPU. A global batch size of 8 is defined, then automatically split across replicas, and a small synthetic dataset with linearly generated labels is created and distributed. Within the chosen strategy, a simple neural network is built, compiled with stochastic gradient descent and mean squared error, and trained for one epoch. After training, the script examines how the global batch is divided, printing how many parts it is split into, the shape of one part, and a sample feature to confirm that the data is sliced correctly across replicas. In this lecture, you learn to describe the main tf.distribute strategies available in TensorFlow 2.20.0 and their typical use cases. Explain how data parallelism and replica synchronization work in distributed training. and identify the changes required in model and input code to support distribution strategies. In the next lecture, Lecture B, we will go over implementing strategies.
Thank you for your attention. See you all in the next lecture.